So in the last lecture, we talked about bonding. We're getting a little bit into these sort of characteristics and properties of electrons, and we basically said that they are within these what we call orbitals that are developed because of the fact that our solution to where they are is in fact a wave function. And so we briefly covered this sort of idea here where we have this nodal plane, and we kind of talked a little bit about how we get the shape of the electron or the bonding region. So the next thing here that we're going to discuss is how we actually get to a bonding orbital, and really what they are. And so we get these by combining atomic orbitals. So each piece, each atom that's going to form a bond has its own atomic orbital. And we get these by combining them into what we call molecular orbitals, orbitals that are formed because of the actual molecule that's made through bonding. So this is what we call LCAO. It's the abbreviation for linear combination of atomic orbitals. And we get these by combining orbitals between two different atoms. And this is, in fact, what we call bond formation. So combining orbitals on the same atom is another term for, basically, is the definition behind hybridization. So we call this hybridization. And of course, one of the things that's a sort of a hallmark of this is that we have conservation of orbitals. We don't throw them away. And we have the sort of addition that can happen in two ways. You can have a sort of constructive or deconstructive addition because we're talking about the addition of waves. So they can cancel each other out or they can add together, right? And so, um, so waves that are in phases add together. And in this case, this would be a constructive addition. So this would mean that here the amplitude increases. And then, of course, waves that are out of phase cancel out. This will be a deconstructive addition or destructive addition. So waves that are out of phase cancel out. All right, so let's see what a little bit of this comes into play and what this looks like. And so let's first talk about sigma bonding. And so when we look at sigma bonding, we of course can think about where the electron density is. And this is, of course, in between the two nuclei. And so, for example, you can have some element and another element, and we're going to form a sigma bond in between these two. The electrons that are within the bond are between the two nuclei of each element. So that's what that guy means. And we can actually form sigma bonds by the overlap of an s orbital with another s orbital, a p orbital with another p orbital, or an s overlapping with a p, or some other hybridized orbital. So here is where it's really important that you understand hybridization. Right? So hybridization is important in this aspect. And so one of the hallmarks behind this is, well, why does it happen at all? Well, it turns out that when we make a bonding orbital, right, so when the individual atomic orbitals come together to form a bond, right, we're getting this lower energy level because the molecular orbital, which would be our bonding orbital, is lower in energy than the individual ones, right? Now, remember that because we're talking about waves, so they can add constructively, in other words, they add together, that is good, and this would be an example of a constructive addition. And this would be when they cancel each other out, right? And so this gives us what we call the antibonding molecular orbital, and it's higher in energy. Okay, so let's look at just in general, just an overall picture of this and what we're talking about. So here's what I was talking about here. This would be basically what I would say would be X, right, on the other slide. And then this will be the other X that we had. And so within this region here, we have this bonding region. Those are where our electrons are going to be. So the electrons here sort of are kind of attracted to the nuclei, and it also kind of pulls the nuclei together, right, so that we don't have this repulsion from the two positive charges of the nuclei, right? So because if you think about it, remember that the nuclei in each atom are positive, and so if they're too close together, then they're going to repel. But these electrons that form the bond are in between those, and so what they do is sort of mask the positive charge, and they're kind of only really feeling these electrons, right? So that's the idea behind this. And so when we look at this, you can imagine that this whole bonding region basically here, this is what we're talking about with our bond, right? These electrons are within here and within this sort of region. Now, we can look at this by looking at an example of this sort of 1s bonding. So what we're looking here is a sigma bond created by a 1s orbital overlapping with another 1s orbital, right? And so here's one here, and here's another one here, and they're going to overlap in constructive fashion, and they're going to give us this bond. And here's what we're looking at here. This is our bond, right? So we would indicate what this is because notice here we have 1s and then another 1s, right? And we form the bond, and so this would be referred to as a bonding molecular orbital that is a result from 1s overlap to another 1s, right? So that's what we're looking at. So an example of this would be hydrogen, right? So hydrogen, of course, is represented by H2, but why? Well, because basically what we have is hydrogen itself. If you look at the periodic table, is 1s1, right? And we said that, it wants to get to that noble gas configuration. Well, it can here by sharing an electron. And so we have a 1s1 that's going to overlap with another 1s1, which gives you the bonding molecular orbital. Now, you can actually see this if we kind of do what's called an electrostatic potential map and calculate out sort of through some. Okay, so we can look at these electrostatic potential maps here, and we can calculate those through quantum chemistry, and they give us sort of this idea and show us what this bonding looks like. So you can see here in this picture, the red is typically what's indicative of electron density. And so we have each hydrogen that's sitting over here like so, and we have this area of red that's right in the center, right? Those are where we are looking at the area of electron density that's in there. So this is just a helpful little map that you can see, kind of like a heat map. And you're going to see these throughout organic also. And just remember that red is where electron density is. Now, we've talked about the bonding portion, we've talked about the constructive overlap, and now I need to look at the destructive interaction here and what happens when they add sort of out of phase together. Well, notice that they add out of phase, that means they subtract from each other, and we end up with something that has a nodal plane within the middle of it, which is bad. If you're trying to form a bond, you don't want a node in the middle of it. Remember, a node is an area of no electron density. And so formation of an antibonding orbital is when two atomic orbitals overlap out of phase. Right, and so whatever bonding orbital we're looking at, so in this case, we're adding a hydrogen 1s1 with a hydrogen 1s1 again, forming the overlap. This would be a sigma bond. And so we would represent this as sigma bond, like so. And when they add out of phase, we add a star to it. So sigma star is equal to the antibonding. Right, and so this is just a picture of it that you can see on the right-hand side. Notice that we have this sort of nodal plane right here in the center. Right, notice that that's not good. Okay, so now what we need to do is sort of put all of this together and look at it in terms of an energy diagram. So where they lie on the scale of energy. We said that this guy, sigma star here, is going to be higher in energy. And you should think of it this way. It makes sense if you look at sort of an energetic approach, right? So you're trying to form a bond. You want those electrons to be together that are in between the two atoms, and you want those there because you need to have something that allows for this attractive interaction between the two nuclei. But the two nuclei from each thing that's going to bond can't be too close because they are positive and they would repel. So what we need then in that case is these electrons in the middle. Now, if they are at the right distance and these electrons are in the middle, then it's going to hold everything together, right? That's perfect and that's what it wants. But if you instead have these guys overlap in an anti-bonding molecular orbital, then there's not electron density between them, so you have sort of an area of repulsion, right? Those two positive charges are going to repel. So that would then increase your energy level, right? And so we can show this when we put all of these together in what we call a molecular orbital diagram. It's just a fancy word of putting it all together like this, right? So we have energy over here on the left-hand side, right? Here's our energy that we see. And we have our individual atomic orbitals. So this is our hydrogen here that we have. And then we have this other hydrogen here. Now, remember that when they bond, they get that noble gas configuration. So they're happy, happy, happy. And they're lower in energy. So it makes sense that when they form a sigma bond, that the energy level here would be lower, right? Now, this is constructive addition, and you end up with your molecular orbital, right? Now, when they add destructively, they're going to cancel out, and there's going to be a node in between. So the energy over here would be higher. And so here's your antibonding orbital up here, right? So all this is just an energy diagram, putting it all together like this, showing what these things look like. And actually, we even simplify it down even more, and typically you're going to put something together like this. Energy, and here's your bonding, and here's your antibonding. So this would be a sigma. And for the case of hydrogen, we have two electrons there. That's indicating this H2 bond that we're forming. And we have no electrons that are in our sigma star. Right? So that's, in a nutshell, the same thing that we're showing here on the right, just even simplified more. So let's look at chlorine. Let's move out of the sort of S and go over here to P. So chlorine is going to form a bond that we see here with two p orbitals. If you look at chlorine's electron configuration, right, you'll see that we have the p orbitals that are available there. And so when two p orbitals, let's just add this in. When two p orbitals overlap along a line between the nuclei, a bonding orbital and an antibonding orbital, just like with the S. All right, we end up with each one of these. And this sort of linear overlap here, again, is another type of molecular orbital, sigma bonding molecular orbital. So this also represents, let's just say, linear overlap also represents another sigma bonding molecular orbital. Right, and so we can depict this in the same fashion that we did for the last one, right? And this time we're going to kind of look at this as sort of how they would overlap together. And so, in a sense, we can see here's our bond right here. This is our bonding orbital, right, where we have each individual one that's there, and we have the same deal. So we have P, and you would just sort of put this into the same diagram. Now, one thing, if we're looking at this, S would be way down here, and we're looking at P. So this would be sigma star. All right. These are formed by the two p orbitals, just not s orbitals, so it's the same thing. You can also have an s and a p orbital overlap, right? So here's an example of that. Right, and so we can form a bonding MO again, just with the same as that guy. Right, so pretty much you can combine these S and P to P and S to S. Those all work to give you the sigma bonds here. Now, the other thing that we need to talk about, though, is pi bonds. And these are, of course, p orbitals that are going to overlap here. And what they're going to do is overlap in the same fashion that we had before, so they can be constructive or deconstructive or destructive. And we can have, of course, bonding and anti-bonding just like that. Now, the thing is if you'll notice, this is not a sigma bond. Remember, sigma is the result of a linear overlap. It's a bad p orbital, but these two overlapping like so in linear fashion. This guy over here is the result of a different type of overlap. Notice that these guys are overlapping like so in this fashion, right? And so these are going to be either your P, Z, and Y that are going to overlap here. And so what you can see over here is we have this guy that's forming our pi bond, right? So this is a different type of bond than sigma. This is now a pi bond. And we have the same deal, though. We can have the pi bonding MO, and we can also have the pi anti-bonding MO. Right, so the thing that's important about this is that these guys are going to form a bond above and below the plane. Right, so if we take, for instance, and we look at, let's just look at ethene. So that's carbon with a double bond. And here's our ethene molecule. And we want to look at the hybridization of any one of these carbons. So this one is sp2. Right, that's our hybridization. So the geometry is trigonal planar, which means flat. Right, and so our bond is actually going to be above and below this sort of area here, right, that I'm drawing there. So this is where we end up with our sort of pi bond and how it looks. Right, so let's sort of take a look at this. I'll get to the next slide here and I'll show you what ethene looks like. So you can see that we have our pi bond. Now notice we still have a sigma bond that's here, right? We have a sigma bond, and we have a pi bond, and we have part of it that's up top and part of it that's bottom. notice that this hydrogen, this hydrogen, this hydrogen, and this hydrogen are all in the same plane, and these dashes and wedges here are here to sort of give us the idea that this hydrogen is pointing more towards back here, while this one is pointing out towards the front of you, right? So into that corner there that's coming towards you. So that's what those look like. And so, of course, this gives us now a double bond, and a double bond will consist of course, a sigma bond, and that's the one in purple that you can see up there, and a pi bond. Now, if we have a triple bond instead of a double bond, remember that a triple bond still has a sigma bond, but now we have two pi bonds. So it's important that you understand the shapes of these and what's happening here. So let's move on down. And the really important aspect of this is that we look at our geometries, because these are important. So here you're looking at these different shapes. Notice that, of course, this hydrogen, this hydrogen, this hydrogen, and this hydrogen are all in the same plane. If we go back to this, each one of them is sort of can be represented as being in one of these corners that we see over here, right? Just like this. Right, so those guys are all in the same plane, and our pi bond is above and below that with our sigma in the middle. Right, so now when we're looking at something that's tetrahedral, where we have only sigma bonds, here we have this guy that has this geometry that has or bond angles that are between each other that are 109.5, and then of course we have roughly 120 for these guys that are ethylene. So this one, of course, would be sp3. This one would be sp2, and then you should be able to fill this one in as sp. Right, and so we get this what we call valence shell electron pair repulsion theory. This is VSEPR that you should have covered in Gen Chem, and these are what explains our bond angles. Right, so the idea behind this is that we end up with these what we call hybridized orbitals. And these are, of course, lower in energy, because the electron pairs are further apart. So let's look at SP over here now that we can talk about this guy over here in this one. S&P hybridized orbitals. And so, of course, we see that our geometry here for this one is going to be linear in this case, right? So we have a 180-degree bond angle in this one. And let's look at what's involved in forming these bonds. So, of course, we can have our constructive or our destructive overlap that we see here. And in particular, hybrid orbitals, what really are they? Well, these guys result when orbitals in the same atom combine. So, of course, in this case, we have two orbitals that come together. Two orbitals. And these guys form two sp orbitals. And then, of course, we see in these sp orbitals that we have, of course, our linear geometry. And this gives us this 180-degree bond angle. Right, so we end up with a 180-degree bond angle on that one. So we can look at an example of this without carbon, and we can look at beryllium and hydrogen. So we have our couple of different orbitals that the really important aspect here that you need to know, and this is what I would probably ask is, well, what is the bond made up of? In other words, what orbitals are giving us this bond, right? And so, of course, we have beryllium that's going to give us this linear structure. So this one is going to be sp hybridized. Hydrogen here has one s, right? And so the bond that we see between these two that gives us this sort of, you can look at these guys sort of overimposed together. This is just a left and a right picture of it. And so what I'm looking at is a 1s1 from hydrogen overlapping with a beryllium sp. Right? This is what's forming the bond. Right? So it's important that you can denote that and look at each of those. Again, hopefully this is a bit of a review for you. But now we need to kind of look a little bit more into hybridization. And we're going to start looking at it with sp2. And basically we have this idea that if we look at S and P and the energy levels. Now, let's move a little forward really quickly to look at something that's sp3, because we've all heard of that. And all right, so if I look at carbon, I know that I have 1s2, 2s2, and then 2p2 as my electron configuration for carbon. Okay, so if I'm looking at where I'm going to form bonds, and we know, for instance, let's just kind of take a look back. We know that carbon forms tetrahedral and 4 bonds with 109.5 degrees here. So I have an issue because here I have, if I look at this with all of my different electrons and energy levels, 1s2, 2s2, and then up here are my p orbitals. Both of these are full, and then one here. Well, right now, that's not a very conducive way to make a bond. Now, one thing I could do so that I need electrons to share. I need 4 places to share. Well, one of these places I can't share because it's full. So I could potentially take this and excite. Give it some energy to push this electron up to here. So if I did that again, I would have 1s2, 2s2, and then up here I would have the different p orbitals. So now I'd have one here, one here, one here, and one here, which now I can share electrons to give me 4 different bonds. However, my question to you is, in this case, are any of these bonds or any of these bonds different than each other? In other words, do they have different energy levels? because this is what this guy would indicate over here. That this bond right here is lower in energy than any of the bonds that are made by the p orbitals that are up here. And we know that that's not the case. So what happens instead of this to explain the fact that we have 4 equivalent bonds is we end up with hybridization. So here's the sort of generic structure that we have at the beginning, and here we're going to hybridize. And now this guy we don't care about, he's too low in energy. And now we have, in the case of carbon here for this one, 4 equivalent sp3 orbitals. And each one contains 1 electron each, which now allows for something else to donate 1 electron, which gives us 4 equivalent bonds. All right, so this is why hybridization occurs, because, again, even if I have just a simple, let's do methane, and again, the dashes and wedges are showing you their sort of positions. It doesn't mean the bonds are different. Right? It means one's coming back and one's going towards you. The wedge means it's coming out towards you. Right? So this tells me because each one of these hydrogens is not different than the other, the bond's not different, and it is more represented by this guy, right, due to hybridization. Okay, so let's look at sp2, and of course we can see that we have sp2 orbitals that are hybridized. One thing that's different about this is that we end up with a p orbital. So I end up here with sp2 orbitals, but then a p orbital. That's important because you need p orbitals to form pi bonds. And we end up with 3 different sp2 orbitals plus 1 that has a p orbital. Right? So sp2, you get, when you hybridize, 3 sp2 orbitals and 1 p orbital. So let's do kind of an example and sort of show you what I would look for something like this. And so here's an example that we can have. So borane, which is BH3, is typically not stable, and actually when you get it, it's actually complex to something else. But let's pretend that we can make it exist just in its raw form. And so what we need to do here are a couple of things, and we need to draw the Lewis structure for borane, and we need to sort of look at its bonding. And in particular, what we want to do is look at the orbitals that are involved in the bonding and also what the bond angle should be. So if you're watching this, which hopefully you are, you should pause it and try to work on this on your own and then restart it and see how you did. So if we're looking at boron, we have BH3. We can draw the Lewis structure, of course, by something like this. H, H, H. Right, so this would be our Lewis structure, which, of course, we're going to represent like this because nobody wants to draw all of those little dots, right? So we've got part A down, and so now we need to look at the bonding, a diagram of the bonding in this molecule. Well, what's important here is to note what bonds are, or what orbitals are overlapping to form the right bonds, right? And so this brings us now, we can see that hydrogen, of course, we know hydrogen is 1s1, but the question becomes, what is boron? Well, boron only has 3, and so something that has 3, for instance, I'll give you just an example if you remember from Gen Chem. if you're looking at 1/2 of ethene, we're looking at number of bonding groups. So here I'm looking at 1 bonding group, 2 bonding groups, 3 bonding groups that's there, right? And so, of course, on the other side would be a carbon with the other, all that stuff on the same, right? So this tells me that, of course, I have sp2, right? So sp2 means I have 3 sp2 orbitals, and then I have 1 p orbital. Right, so if we want to look at the bonding diagram, and this is what we would be talking about here, we have boron in the center, and I'm going to have something that looks like this. Hydrogen, hydrogen, hydrogen here, right? So boron is there with this guy, and so note that what I have in each one of these bonds, I have sp2 from boron overlapping with 1s from hydrogen, right? So this is the sort of bonding diagram that I'm looking at there, right? These are the orbitals that are involved in the bond. Now, if we're looking at this, we know that it's sp2, so we need to predict the bond angle at the end of the day here. Well, everything should be around all of this, right? Everything should be 120 degrees, right, as our bond angles there. Okay, so now we can move on over here to, of course, sp3. We kind of earlier talked about this just very briefly. And I gave you, of course, the reason behind hybridization. So remember that sp3, we're going to get 4 of these, right? So we get 4 sp3 of these guys, and we end up with a bond angle that is 109.5, right? So again, you get to these sort of, is it sp, sp2, sp3? You get these by counting bonding groups, right? So in this case, when you have 4, and you're in particular talking about carbon here, you have 4, we're going to have sp3, right? So that means we need 4 bonds. And a perfect example of this is, of course, methane. We have 109.5, and again, all you do is you're going to count your bonding groups. So we have 1 bonding group, 2 bonding groups, 3 bonding groups, 4 bonding groups, right? That gives us this deal here. And so, of course, we have 109.5 as this guy, as our bond angles, and we have 4 equivalent, that's important, 4 equivalent bonds that make up methane. Now, bonding diagram for this guy. Look over here, sp3 to hydrogen 1s. So if I were to ask you what orbitals are involved in the bonding, you would tell me, in this case, you would say a carbon, sp3, overlapping with a hydrogen 1s, right? This is what we're seeing here for these bond, the orbitals that are making up the bond, right? And so all you need to do, again, is count bonding groups, and that tells you what you have, right? So just as a summary, right, notice here we're going to look at this, and you can see these that are down here. We have our bond angles, right? Over here on this guy, we have our geometries. And so we're looking at, in particular for carbon, mostly we're going to look at linear, trigonal planar, tetrahedral, right? And we're looking at this guy here with bonding groups. And so I'm going to give you just a brief. We have methane, and we have ethene, and finally acetylene. You need to make sure that you're familiar with this acetylene or ethine. Make sure you remember what that is. And again, all we're going to do here is count bonding groups, right? This tells us what we have as far as hybridization. So 1, 2, 3, 4. That tells me sp3, trigonal planar. Here I have 1, 2, and then all of this counts as 1. This tells me I have sp2, 120. Here I have only 2, 1, 2. That gives me sp, right, which means I have 180 or linear. So if we were to sort of take it out and do it a little differently, what if I asked you for formaldehyde? what would you say would be the hybridization and the bond diagram for this? Well, you go about this in the same way. One bonding group, two bonding groups. This whole thing is three bonding groups. I have three here, so this means it's sp2. We need to predict the hybridization here of ammonia, and we need to draw the three-dimensional structure of ammonia and predict the bonding angles. So again, you should pause the video, do this on your own, and then come back to this. So of course our Lewis structure would be this guy. We have a lone pair. Remember, nitrogen forms three bonds with one lone pair. And we represent this in the lazy fashion with lines. It looks like this guy. So the question becomes, what is the hybridization of nitrogen in this case? And just like before, we're going to go back and we're going to figure out this by bonding groups. This counts: one bonding group, two bonding groups, three bonding groups, and four bonding groups. So that means that hybridization of this guy should be sp3. So if I'm looking at what these bonds should be, I should see the overlap nitrogen sp3 to hydrogen 1s. These are the bonds that I'm looking at there. Now, nitrogen itself, because it has this lone pair, this lone pair on it, like so, you can kind of envision it like this. This guy here is sort of pushing down a little bit, and so your bond angle is going to be a little less than the favored 109.5. So it is actually 107.3. But as long as you give me something close to 109.5 in this case, I would accept that. Not a problem. All right, so let's move on now. Let's look at ethene, right? And so, of course, here in this case, we're looking at the double bond that we see. And we have some two bonds that we have to deal with in this case. And we have to deal with, of course, our sigma bond, which is this guy, right? And so we can see that in this case here, we have carbon sp2 overlapping with carbon sp2, right? That's our sigma bond. But then we also have our p orbitals, and our p orbitals sit up here, right? And they're above and below the plane of the molecule. And so you can see the picture that looks like this. Look, one on the top and one on the bottom. These are not different. These are equivalents, right? So you just have to remember that they're above and below because of the nature of the p orbital, right? So here we can see that, of course, we're looking at two separate bonds. We have a sigma and a pi bond, right? We have a carbon sp2 overlaps with carbon sp2, and then we have our pi bond, which is p overlapping with p up here at the top, right? So again, what about this one, this bond that we see right here? Well, that's carbon sp2 overlapping with hydrogen, which is 1s, right? So that is bonding in ethene. Bonding in acetylene, also named ethine. Right, remember that in this case here, we have two pi bonds, and we get this because we have a py and a px, right? So we still have our sigma bond, which is carbon sp in this case, overlapping with carbon sp, and then one pi bond, so I'll just put pi 1, is the result of one p overlapping with the other p orbital, and this one would be a y, up and down, right? And then coming out towards you here, you can see this, that you have pi 2, which is from the z-axis. So p overlapping with p again on the z-axis there in that case. And this gives us our sp hybridized carbon with a linear geometry Now, one thing that we need to discuss when we're looking at different bonding here, or different types of bonds, is of course rotation. Rotation in single bonds. You can absolutely rotate these single bonds. Notice here, this guy can rotate all the way around. All right? So it doesn't really matter. It rotates based off of energy, and these are what we call different conformations. They're the same molecule, they're just in a different conformation from each other. So if I rotate here, notice that I've got this one down and this one in the back still up, right? And so we have some names for these, and when they're sort of eclipsing each other like this, you can think of, typical eclipse, right? One's blocking the other, and we'll discuss this more in lecture actually later. But notice that we have this rotation. There's actually an important aspect about this in that because single bonds can rotate, you have different energy levels that the different conformations exude here because of that. Right? So this is something that we'll talk about a little bit later. But notice that in single bonds, you can in fact have free rotation. Right? So single bonds. Double bonds, triple bonds, no rotation. And that is because we are basically locked by this guy here. Right? In order for you to have a rotation about this, you would have to actually break this. Right? So this guy can't move. So no rotation about pi bonds. Right? So double and triple bonds, you can get no rotation. The only way that you can rotate these is if you were to move them. All right, so this is important because it gives rise to some different issues. In particular, this gives rise to isomers. Right, so because double bonds can't rotate, this gives something we call isomerism. Right, so what is an isomer? An isomer basically falls into the category of molecules that have the same molecular formula but differ in the arrangement of their atoms. And we have really two kind of types that we can really deal with. We have constitutional isomers. These are also what you can think of as structural isomers. These guys differ in their bonding sequence, so their connectivity. And then the other one that we have are what we call stereoisomers. And these differ only in the arrangement of atoms in space. This is what happens when we look at these double bonds. Because they can't rotate, they fall into this category that's over here, stereoisomers. So just as a quick look here, we have, of course, constitutional isomers. These are the ones that are just kind of put together differently. So for instance, in this case, I can look at pentane, right? So CH3, 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 I'm sorry, 2, 2, H2, CH3 down the end, right? So I have carbons, 5 carbons, 1, 2, 3, 4, 5. 12 hydrogens. And this would be pentane. But I can still have other structures that have the same formula here, but look different than this. So for instance, here I have C5, still have 12 hydrogens, but this is definitely different than the other one, right? So this one will be called neopentane. And this will be an example of a constitutional isomer, right? So I can also put this together differently as well. I can have isopentane, right? So I still have C5H12 again, right? So still, right? And so this is isopentane. So this is an example of a constitutional isomer, right? We have the same formula, but they're connected differently, right? So I'm going to just skip down to here. And then this is where we look at things, for instance, with the double bonds. So for instance, if we look at this. So we talked about double bonds that cannot move, right? I cannot have rotation. So I put CH3 up here. And on the other side of the double bond, I have CH3. And of course, we add our hydrogens in here. But what about if I did it differently, where I put, in this case, say CH3 up here, and this one a CH3 down here? Well, notice that these basically, everything is connected the same way, right? I'm still connected to this carbon. This, even though one's up and one's down, they still have the connection at the carbon that you see right here, right? So they're not connected differently, but there is in fact a difference about it, and that's because I can't rotate this double bond. This piece can't rotate around, right? Because I have that sort of locking pi bond that's up there, right? And so this is what we call a cis-trans isomer, and these are also types of stereoisomers, and we can refer to these as, in particular, geometric isomers because they have a different geometry, right? And so this one will be cis, where they're on the same side, right? Both of these are up. In this case, they're trans. Here, one's down, and this one's up. So this is trans. And so these, again, fit the category of being a stereoisomer because they have the same connectivity, right? They're just oriented or arranged differently in space. And you can see that here, that this one is, both of these are up, and this one, they're both down, but they're still connected to the same carbon, or one's down and one's up, and they're still connected here to this carbon. This one's still connected to that carbon. So we have the same connectivity, but they're clearly not the same. And so this is where we refer to these as geometric or stereoisomers, right? And in particular, these are even more specific as a stereoisomer because these have a different geometry, in other words, cis and trans. All right, and that will do it for chapter 1 for us. So thank you for paying attention, and of course, I will be there in office hours to answer any questions that you should have.